Okay, so today we're gonna go over phase diagrams. You see this. So this thing right here is the phase diagram, and there's a lot of information, but we're gonna take everything one by one and slowly let you guys know what a phase diagram shows you. So a phase diagram will tell us what state a compound is in at specific temperatures and pressures. So in order to figure out what state, let's say, water is in at a current conditions, we need to know what the temperature is, typically in degrees Celsius, and what the pressure is in terms of ATM. So for example, if I had asked you what is the state of water at 100 degrees Celsius at a pressure around, let's say, 50 ATM. So based on the information, we see 100 degrees Celsius right here. And let's assume 50 ATM is right around here. So we head up, and where the two pieces of information meet will tell us what the current state of water is. So water is a liquid at 100 degrees Celsius and at 50 ATM. Now usually you guys think that like 100 degrees Celsius means water is boiling. Well, that is if the condition that the pressure is currently at 1 ATM. At 50 ATM, water is actually at in a liquid state. Another example, let's say we have water at, let's say, negative 20 degrees Celsius. So let's assume negative 20 degrees Celsius is right here. And we have a pressure of 1 ATM. So right here, we have 1 ATM, and it meets at the negative 20 degrees Celsius right here. So the current state of water is currently solid. So if you guys notice, typically this area down here is always in a gas state, while the area up here is always in a liquid state, and the area to the side over here is typically always in a solid state. And that's because at low temperatures we usually get a solid, which is very true. At high temperatures we usually get a gas, and usually it has to be in low pressure. And then for high pressure at somewhat intermediate temperatures we get a liquid state. So why is that so? Well, that's because typically when we think about so how does pressure affect your current phase? So pressure will affect your current phase because it affects how packed the atoms are. So in high pressure, all the atoms are much more packed, and so therefore it is more likely to be a solid. While in low pressure, we kind of like force the atoms to become farther apart from each other. So because atoms are further apart from each other, typically it's going to be a gas. So if we go back here, you'll see that this area is a gas because it typically has a very low pressure. All the atoms are very spread out, and therefore, because of the low pressure, it is more likely to be a gas. At higher pressure, it's more typically going to be a solid or a liquid, because the pressure forces the atoms to stay near each other, and therefore it gives chances for the IMFs to really interact with each other and create the solid or liquid. Now the second thing is we have temperature, and this affects how quickly the atoms are moving. So you guys should already know this. So if the atoms are moving a lot quicker, they're more closer to a gas state, while if the atoms are slower and not very moving, then it's more likely to be in a solid or liquid state. So going back to this, we see that at higher temperatures, we see gas. At intermediate temperatures, we will see liquid, and occasionally gas at, remember, low pressures. And at very low temperatures, we will see the solid. So, based on this, do you think it's possible to boil water without changing temperature? So, can you get water into from a liquid state into a gas state without heating it or adding energy whatsoever? Just pause the video, take like 10 seconds, and think about if that is possible. So, it is actually possible to boil water without changing temperature. So, let's use room temperature. Room temperature. So we have 25 degrees Celsius at 1 atm. This is usually the condition for room temperature. So we have 1 atm, and then we have 25 degrees Celsius. So water is typically a liquid state under these conditions. So if you have to keep the temperature, the way you can force this water to turn into a gas state and therefore boil would be to lower the temperature down to where it will officially be a gas. So let's assume right here. So by dropping the pressure down to 0.006 atm, we can force liquid to turn into a gas state and therefore boil. So, not only does this phase diagram tell us what state the specific compound is at specific temperatures and pressures, but also lets us know when it will boil, when it will freeze, when it will melt, and all the other phase changes you learned yesterday. So, for example, as ice turns into water, we are melting, and as water turns into ice, we are freezing. Therefore, this line right here represents the freezing and melting points for ice and water at various temperatures and pressures. And the same, through the same concept right here, where liquid turns into gas and gas turns into liquid, so through condensation and evaporation, this line will therefore represent the boiling point and condensing point for water. And lastly, we have this area right here where solid meets gas. So this is where sublimation and deposition will occur. Now, typically at these lines, so how do you know at this line whether it's technically a solid or a liquid? So the cool thing about these phase changes is that at these lines, the two states that meet at these lines both exist at that line. So at this point where the boiling point exists, or the melting point, you will have a solid and liquid state occur together. In the same way, at the boiling point, you have water and gas appearing together, and at sublimation and deposition, you have the solid and the gas occurring together. So now we have the triple point. So the triple point is where basically all these three states of matter exist at once. These instances can be freezing, boiling, melting, and condensing all at the same time. So where all these three phases meet right here is called the triple point. And at this point, similarly to how all these lines have both states of matter existing, at the triple point, all three matters will exist. So the next part is the critical point. The critical point is the point when gas and liquid become indistinguishable. So right here we have the critical point, and so anything beyond this temperature and anything beyond this temperature and this pressure we come to a point where gas and liquid become indistinguishable. Both states technically still exist, but you will not be able to see the difference between them. And you guys can watch the video to see what that's like. So, I want you to take a few minutes, pause the video, and just try out these three practice problems. And the graph you will need, the practice problems we're referring to are right here in the previous slide. So what state is compound X at point A? So at point A, we see that it is in this area right here, and since it's a low temperature zone and with varying range of pressure, we know that compound X is a solid. At what point is triple B? So if you look at the graph before, you see where all three areas will meet, and that's the triple point, and then that is point B. If compound X is at point G and pressure was lowered, what phase change would occur? What if temperature was lowered? So if you go back to here and you see point G, so you have point G right here. So if pressure was lowered, this point will go down to here. Oops. This point will go down to here, and since this was a liquid state before, it will turn into a gas state, and therefore evaporation will occur. Now, if temperature was lowered, we would go from this point right here to this point over here, and therefore it's going from a liquid to a solid state, and therefore freezing is occurring. And you guys have homework that you can try out. Mr. Shan has posted the Google Doc as well as the key.